So, welcome to massive open online course on chemical process intensification. So, we are discussing something about the process intensification by monolithic reactor as a module 7, and under this module 7 we will discuss something more about this monolithic reactor. In this lecture we will discuss some hydrodynamics, transport processes of monolithic reactor, and this lecture will cover this different aspects of hydrodynamics. You know that how the liquid will be distributed throughout the monolithic structure, and what will be the hold up of the phases, how the friction or pressure drop is taking part in the chemical engineering process based on this monolithic structure, and also what are the mass transfer characteristics whenever any chemical engineering process will be carried out through this monolithic reactor. So, we will be discussing about that mass transfer characteristics also in this lecture. Now, before going to that, we have to recall again that what is that monolithic structure, what is that. So, from the concept of structure, architectural structure of that ancient age, the concept is converted to the present chemical engineering process by developing different structures of that monolithic structure to actually utilize this for the chemical engineering process as it for the process intensification in that particular chemical engineering processes. So, based on that structure, we are getting different types of structure of monolithic like honeycomb structure, even you can say that some other square based oval shaped structure, microchannel based structure, different structure. Already we have discussed the how that different type of structure of monolithic reactor are being actually procured, and what are the different methods that we have discussed in the previous lectures. And also we have discussed more about that what will be the actually application of that monolithic structure for that particular chemical engineering process based on the process intensification on this particular type of structured reactor. Now, whenever you are going to perform any chemical engineering process for the process intensification in this particular type of monolithic structured reactors, you have to know something about the hydrodynamic characteristics, what will be the flow behavior, how liquid will be distributed, what will be the pressure drop, how mixing is happening inside the reactor for this particular shape of these reactors that you have to know. Because this basic understanding of those hydrodynamics of monolithic reactors is essential, because of for the design of their particular reactor and its scale up, scale down, and also performance of the reactor. So, those things are of course important before going to install that particular monolithic reactor in a particular process in industry. And in that case, what are the different factors that affects on that particular hydrodynamics, like that the changing of hydrodynamics based on that geometric shape of that monolithic structure, even operating variables, even some geometric variables like whether it is the square shape microchannel or oval shape microchannel, or you can say that rectangular shape microchannel or other various types. That depends on that geometry, how you are giving of this shape of that monolithic reactor, and those factors actually will affect the hydrodynamic characteristics in the reactor. So, we can say that the changing of this hydrodynamic is one of the important influencing factor under periodical liquid flow rate in the monolithic catalytic reactors, and they have minimal axial dispersion and back mixing in the slug flow regimes, that particularly for the microchannel based structure of this monolithic reactor, that is called honeycomb structure of that monolithic reactor. In that case, microchannel based that procurement is being done for that special type of this monolithic reactor. There actually the efficiency of this reactor is being calculated based on that that mixing characteristics of the fluid, and that mixing characteristic of the fluids depends on the flow pattern of this fluid through the that channel based reactor. So, in that case the slag flow regime is one of the important flow characteristics there, because for the microchannel based reactor only this type of slag flow regimes can be obtained, where you can get that minimum back mixing of the fluid phase in this particular slag flow regime. And monolithic structures also essential a single structure with many thin vertical even parallel channels separated from each other by the walls, and in that case the channels are usually rectangular, but sometimes it may be triangular shape, sometimes it will be hexagonals, and sometimes it will be some other complex different geometries. They are based on that that how investigators or researchers are getting the performance of the reactors variance from the conventional reactors. So, in that case, to increase the surface area and the internal fins are the main that aspects to increase that that performance of the reactor, and that is why that the geometry is the main factors to get that the performance of the reactor based on the creation of the surface area by that internal geometry. And in this case fins is one of the important geometrical effect, where it can give a stabilizing effect on the gas liquid flow and allow the operation in counter current mode without flooding. So, that is why the that internal fins are sometimes be advisable to procure or design that reactor to get that the stabilizing effect in the reactor. And hydrodynamics of such a specialty monoliths will be different from that of the straight channel monoliths in that case. So, these are the different geometrical effect on that performance of the monolithic reactors. And you see that various geometric parameters that is related to the monolith here, like you will see that if you are considering that channel based monolithic reactor, there you will see there will be certain that geometrical shape there, as shown in figure here, some channels will be there, cross section of a single cell will be there. In that case, the number of channels per cross sections that will be typically ranges from 100 to 1200 per square inch. That is denoted by CPSI. So, how to calculate that CPSI? That it is actually denoted by that n, and it will be as 1 by L square as given in equation here in the slides, where this n is called that number of cell and L is called the length from one channel wall center to the other. They are as per figure shown in the slides here. So, high cell density gives high surface to volume ratio and a short diffusion length of gas through the liquid, which will be that suggested for the that better performance of the monolithic reactor. For example, a monolith with a cell density of 600 CPSI, an open frontal area of such as an example 82% has a surface to volume ratio of 3476 meter square per meter cube. So, you can say that if you increase the that cell density, then you can have that more performance to get the that more surface to volume ratio there, and you can get that more mass transfer for that particular chemical engineering processes. So, you can get the more output of the either reactions or some other physical processes also. Now, what is that open frontal area? That is very important, because the cell density that depends on that open that frontal area, that because this open frontal area will give you the measurement of that surface to volume ratio there. So, the void fraction is frequently expressed as the open frontal area. The range that varies between 0.5 to 0.9. So, we can represent this open frontal area as OFA. This is a function of number of that cell, and also what should be the length L, and also width of that channel that is given there. TW, it is given here as shown in figure earlier slides, that here TW is nothing but the wall thickness here, and L is called the length from one channel wall center to the other. So, it is a function of that L, TW and N. So, this open frontal area can be calculated from this equation given here, that OFA will be equal to N into L minus TW whole square, and that can be simplified upon substitution of this value of N from the previous equation, that then finally we can get that open frontal area will be equals to L minus TW by L whole square. Typically, you can say the values for the wall thickness range is between 0.006 to that 0.005 centimeter. So, in the monolithic structure is generally characterized by this wall thickness and the cell density, which are independent of each other there. So, you have to remember that though this cell density and this wall thickness are not related to each other, but these parameters will give you that void fraction, that is called open frontal area, which is actually directly influence the mass transfer coefficient for that particular chemical engineering process. Any chemical engineering process, whether it will be physical or chemical processes, there of course that mass transfer will happen either in with reactions or without reactions. Then that mass transfer coefficient is related to this that geometry as well as that frontal area. That means, here that void fraction of that particular phases which is passing through that that cell. So, that is why cell structure, cell density, cell that cross sectional area will be the geometrical effect for that particular chemical engineering processes output. Now, geometric surface area, that is also important, because how you will calculate that geometric surface area, which is actually responsible for that particular that mass transfer between the surfaces. So, that geometric surface area again it will be a function of that number of cell, that is cell density, and also that wall thickness, length from one channel wall to the other, and also one important factor here that will be called as that fillet radius there, because that fillet radius will give you that particularly what should be the that hydraulic diameter, and based on that hydraulic diameter you have to that analyze that frictional resistance as well as mixing characteristics and other operating characteristics of that monolithic reactor there. So, geometric surface area can be calculated by this equation here, whereas that hydraulic diameter it will be as that 4 into OFA by GSA, and it will be equal to L minus TW by 4 upon simplification. So, you have to remember this, how to calculate that hydraulic diameter for this monolithic reactor. Once you know that L and tau W, then you can easily calculate what should be that hydraulic diameter. Now, what are those hydrodynamic characteristics that I told, that several hydrodynamic characteristics that actually affect the performance of the reactor. So, first one is that flow pattern. There are several different types of flow patterns. We know that for gas liquid operation, we know that plug flow, slug flow, bubbly flow, even annular flow, even we can say that stratified flow. There are several different types of flow patterns. And for liquid also we are getting different types of flow pattern there, and gas, liquid, solids, 3 phase also we are getting that churn, turbulent, homogeneous, slug flow, plug flow, and that particulate flow. There are different types of flow patterns. So, those flow patterns actually will give you that different types of mass transfer efficiency, even reaction performance, and then overall that reactor efficiency for that particular chemical engineering processes. And also another important hydrodynamic characteristic is the flow distribution within the catalyst bed. Since the monolithic reactor is nothing but that bed of the catalyst as a channel or surface with a particular structure. So, how that flow will be distributed through the channel, that should be the important factor for the analysis of performance of the reactor. And another thing is the dynamic gas hold up. Whenever gas liquid reactions will be carried out through this reactor, then what should be the hold up of that gas, what should be the liquid hold up there inside the reactor, that also to be important to be noted down, because those things also directly or indirectly related to that performance of the reactor. And pressure drop is another important factor at a particular pressure, that whenever reactions or that mass transfer characteristics will be carried out, that you have to know that how the flow will be getting that resistance through the reactor, that may that effect on the mass transfer characteristics. Again, if you are considering that gas liquid flow through the channel, there may be that bubble slug or gas slug, liquid slug. So, in that case you have to know the size of that particular slug. That slug may be, you can say that bubble slug or bubble size in that case, and also liquid slug size and their velocities, how actually those slug will be flowing through the channel, that should be actually considered to study. And also if the bubbles are forming there inside the channels, then how it will be break up and how it may be coalescence to get that elongated bubble size there. So, that also to be considered as an hydrodynamic characteristic. And then interfacial area density also through that monolithic channel for particular volume, that what should be the surface area which is taking part for that particular reactions or chemical engineering processes, that you have to calculate as a density, that is interfacial area density. And also power dissipation is important, what of the consumption of the power, that also to be considered, because the performance of the chemical engineering processes in that particular reactor should be economic. So, what would be the power dissipation, that also to be considered as an hydrodynamic characteristics here. And residence time distribution, of course, that is very important, the how long that phase will be residing through the channel for that particular chemical engineering processes, whenever that gas liquid reactions or liquid reactions or gas liquid solid reactions, they are in presence of this monolithic catalyst. So, in that case residence time of the each phases should be required to know. And also stability phenomena, whether these monolithic structures are stable or not. So, that is why these are the different hydrodynamic characteristics which is very important to know for getting the performance of the that reactor, and also that different aspects of the reactor for designing of that particular structure based on this hydrodynamic characteristics. Now, so what is to know that based on the hydrodynamic characteristics, you have to first the catalyst synthesis characterization, after that monolithic structure to be procured, that already we have discussed how to procure that monolithic structure. And also after procurement of that monolithic structure, that you have to study the different hydrodynamic characteristics, based on which you have to analyze the mass transfer characteristics of that particular reactor, and upon which you will be able to that say what will be the efficiency of that reactor for that particular processes. Now, we will discuss something about that flow pattern hydrodynamics there. So, different flow patterns we have told that can be observed depending on the interfacial configuration at different flow conditions. And now single phase flow pattern, sometimes it is happened in the structured reactor, like single phase patterns, only liquid or only gas may be there, a liquid slug will be there, or only single liquid will be flowing without making any slug there. And also two phase flow patterns, there you can have that capillary bubble slug, slug flow of the liquid, even also annular flow. That means in core regions there will be a one phase, and in the that wall regions there will be another liquid there. So, there the annular flow will be there. Churn flow, there will be intermixing of the fluid particles at higher flow rate, then churning of that phases will be happen. So, it is called churn turbulent flow. And then also other factors, it is called transition, whether it may be that annular or slug, particularly that transition, it may either slug or annular. So, in that particular operating condition, you may get that slug and annular more mixed there in a particular operating condition. So, that is called transitions. So, for air water flow through the parallel monolithic channel, you are having this type of flow patterns like capillary, slug, annular, churn, and their transitions. And here one typical flow pattern map is shown there. As per Barreto et al, they have actually given this flow pattern map for this monolithic reactor. They have published this data in experimental thermal and fluid sciences in 2015. As per their experimental observations, they have concluded that the variety of single phase and two phase flow configurations can be observed for the different time steps at the same micro channel of monolithic structure. And they have actually made one flow pattern map. Flow pattern map, what is that? This is nothing but the graphical representation of the transition of different flow pattern that is observed in that particular channel. So, that things are actually represented in a graph, that is called flow pattern map. Now, in this flow pattern map, we are considering that there will be x axis is here, Jg means here superficial gas velocity, and Jl which is denoted for superficial liquid velocity. So, if there is a gas liquid operations through that monolithic microstructure reactor, you will see that at various that gas and liquid velocity, you may have different types of flow patterns there. So, if you increase the gas flow rate by keeping your liquid velocity constant, then you may have flow patterns from bubbly to slug, or slug to churn, or churn to annular flow. Whereas, in the opposite way also you can have those things, like that if you increase the superficial liquid velocity by keeping your gas velocity there, then you can have this sometimes that churn turbulent flow to the slug flow, even to the bubbly flow, even from its the annular flow also. So, from this map we are having different that data at different points at different operating conditions, and here you will see that blue line is actually showing that transition data, where the transitions are from bubbly to slug, or slug to churn, or churn to annular. So, if you are considering a particular point here in the graph, like here, you will see that at this point what we are getting here, what will be the that gas velocity and what is the liquid velocity there. So, at this point, at this gas velocity and at this liquid velocity, if you operate those monolithic reactor, you may get this bubbly flow of pattern there. Even if you keep this gas velocity constant, and if you increase the liquid velocity up to this, then you may get again that bubbly flow pattern. Again, in this way, if you keeping your gas velocity constant and liquid velocity increasing, then you may have this region of this bubbly flow pattern. So, at any point of this region, that means at the combination at the point of this J, G and J L, then you may expect that it will be a bubbly flow regime. Whereas, at this location, if you consider a point here, what will happen here, the gas velocity is little bit higher, and also from this point liquid velocity is little bit higher. So, at higher gas velocity and liquid velocity compared to this previous point of this bubbly flow, you may expect that slug flow. So, this slug flow, it will happen here at this combination. You may get this slug flow here itself also. In this point also, what will be the gas velocity little bit higher, and also liquid velocity also little bit higher, but in this case also you may get the slug flow. But if you consider the point here, this is the transition where at this gas and liquid velocity you may get the that optimum value, or you can that maximum value of this gas velocity, and where you may change the liquid velocity so that you can get this bubbly flow to that slug flow regime. So, here this is the point, these are the point from which you can say at this particular operating condition of gas and liquid velocity, you may get that transition of this bubbly to slug flow. Similarly, again if you increase the gas velocity from this from this point to this, you may expect this at the same constant liquid velocity as earlier. At higher gas velocity, you may get this churn turbulent flow instead of slug flow. Even if you increase that gas velocity and if you consider the point here, you may get that liquid velocity. So, in this way, by just getting the that data point of that gas and liquid velocity, and considering that you may get that you may expect or speculate what type of flow pattern will be there. So, this flow pattern map will give you that expected flow pattern during your operation. So, before going to experiment to study different hydrodynamic characteristics, then you have to that fix a certain gas and liquid velocity for that particular that chemical engineering process. That process may be feasible in the slug flow, that process may be feasible in bubbly flow. So, accordingly you have to select that particular gas flow rate and liquid flow rate to get that particular flow pattern. So, that can be obtained by this flow pattern map. So, this is the importance to study this flow pattern map, and also this you have to utilize for that study of different hydrodynamic characteristics and mass transfer characteristics based on the flow pattern. So, I think it will be very helpful for your analysis of chemical engineering process based on flow pattern, and also what should be the particular operating conditions there. Now, typical results on flow pattern, like for gas quality is greater than 0.1. What is that? Gas quality is also important factor. In this case, gas quality means what is the mass ratio of that gas to the mass of the liquid there, mass of the gas and liquid mixture there. So, that is called gas quality. That means mass of gas divided by total mass of gas and liquid. Total mass of gas and liquid, if is there a gas and liquid mixture flowing through the channel. So, in that case gas quality will be considered like this. So, this is called gas quality. So, if this gas quality it is denoted by X is greater than 0.8 and mass flux, that means velocity into density, if it is 50 kg per meter square second, then you may expect that only single phase flow, that is only air, and in that case that you may expect along with that single phase flow with annular churn and slug patterns. So, for gas quality, if it is less than 0.04 and for every mass flux value, single phase flows only water may be resulted along with bubbly or slug, churn and annular configurations. And for gas quality, if it is greater than 0.08 and mass flux if is greater than 100 kg per meter square second, a clear view of the annular flow pattern can be obtained. And this actually roughly corresponds to the superficial gas and liquid velocities over 10 and 0.1 meter per second respectively at the inlet manifold in the monolithic structure. So, you actually can optimize on which gas quality to be maintained to get that that particular flow pattern. So, these are observations based on that experimental results actually obtained by Barrett et al. In 2015. Now, how to control those flow pattern? The flow regimes can be, or flow regime, sometimes flow pattern it is called flow regime. So, this flow regime can be controlled by that gas and liquid superficial velocities, hydraulic diameters of the monolith channels and the liquid and gas properties. In the parallel channels, when heating is applied, vapor is generated, and in that case the system may become unstable, and often you can get different types of flow patterns or regimes. And in that case you may expect the flow pattern of incipience of individual bubble, nucleating pattern, slug flow or clusters of liquid droplets, and this is reported by Hedstroni et al. In 2003. They have published their work in the International Journal of Multiphase Flow in 2003. So, for steam water flow through the parallel monolithic channel, you may expect this incipience of individual bubble, nucleating pattern, even slug flow, clusters of liquid droplets. These are the different flow patterns you can expect in this particular type of channel. Now, flow pattern or other also may be happened and that depends on that geometry of that channel. So, bubbly flow can be observed in monoliths at low gas and high liquid superficial velocities. Slug flow, churn flow and annular flow that may occur at high gas and low liquid superficial velocities. As per Roy et al. In 2004, they have actually published their experimental work and observations for that flow pattern study in monolithic structure, and also the annular flow pattern which roughly corresponding to the superficial gas and liquid velocities over 10 and 0.1 meter per second respectively. That is also observed by that Coleman et al. 1999, that is reported in that in the review paper published by Roy et al. In 2004. Flow pattern also that enables to enhance the mass transfer rates in reactive multiphase flow, especially slug flow regimes are very important in this case. In that case by controlling the interfacial area via the flow pattern, you can enhance the mass transfer rates as per Leclerc et al. In 2010, and also you may expect the enhancement of the mass transfer rates in reactive multiphase flows in case of that mixing characteristics, where a good mixing within the slugs due to the recirculation and short diffusive path through the liquid film at the catalyst wall. That is actually given by Kaptizin et al. 2001 and Abib et al. In 2011. And there are several operating mode and flow distributions are observed in the monolithic structured reactor, where you can say that the operating mode and flow distribution have strong effects on the performance of reactors. The reactor can be operated in batch and in continuous modes. In the batch mode, liquid is continuously circulated through the monolith unit until the desired conversion is made. And in the continuous mode, the liquid flows only once through the monolith core is there. So, there are 3 different flow arrangements possible in that case: co-current downflow, co-current upflow, and the counter current flow. So, there are different that operating mode, and the flow distributions are happens in that in monolithic structured reactor. Now, question is that why you have to know that flow distribution in the monolithic reactor, because the uniform flow distribution in the multi-phase flow reactor is very important for enhancement of the productivity and selectivity. It generally ensures complete use of catalyst and prevents hot spots in an exothermic reaction system. So, that is why you have to know the flow distribution, whether this liquid is distributed properly or not, whether there any that stagnation of that liquid in the channel or not. That stagnant region may sometimes that hinder that performance of the reaction, and also that may that reduce the intensity of the mixing inside the reactor, for which that mass transfer will be reduced. So, the importance of gas and liquid distribution inside the monolith is much more profound, and which is to be that analyzed. And unlike random packing or other structure packing, once the liquid enters the reactor, there is no further redistribution inside the monolith reactor. That is as per that structured packing. Therefore, the liquid must be distributed uniformly before it enters the monolithic bed. Now, different types of distributors sometimes be used to achieve those desired uniform flow distribution over the monolith cross section, like for downflow, for upflow mode, what are the different distributors are being used for the distribution of the phases in the reactor. For the downflow, generally spray nozzles, shower head layer of spheres monolith, even sheet plates, discs, glass frit, ejectors. These are the different distributors are being used for the distribution of the liquid. And for upflow, whole plates, that glass frits and static mixer are being used for that flow distribution of the liquid through the monolithic reactor. Shower head layer of spheres monolith disc, generally it is a layer of monolithic disc that actually give the reproducible pressure drop values indicating uniform distribution. Whereas, glass frit distributor produces froth, which then travels up, and overall monolithic activity achieved may be same as intrinsic rate, that will indicate the uniform distribution. In case of liquid driver ejector type of distributor, the ejector action produces fine gas bubbles in the liquid, which may be easier to distribute throughout the channel to get that more interfacial area between gas and liquid, to get more mass transfer efficiency in that particular chemical engineering process. Now, with increasing liquid velocity, sometimes the quality of the liquid distribution increases, but sometimes it may be decreased because of that design of that channel. If you are design that channel with some internals to get that more mixing there, that may sometimes give you that static region of that liquid. So, generally increasing liquid velocity, the quality of liquid distribution increases, but if there is a special structure where that you are actually inserting some internal there, sometimes it may give you that some stagnant region. So, if you are optimizing those stagnation factor for the liquid distribution, then you can get that enhancement of that mass transfer based on this liquid distribution. A well established phase distribution delivering the optimal amount of liquid per channel, that can be used to tailor the partial wetting characteristics sometimes. So, you know that you have to design that reactor where that phase distribution may be optimal amount of liquid through that channel, and for the characterizing the partial wetting there during the flow distribution. And beneficial for the controlling mass transfer resistance are most important, because that depends on that flow characteristics like flow distribution through the channel. So, that is why flow distribution is one of the important beneficial factor for controlling mass transfer resistances. And this flow distribution, how you will actually estimate experimentally, you may or you can use that computed tomography system and magnetic resonance imaging system for the observation of the liquid distribution in the channel, and you can analyze it by different that suitable model to predict that particular intensity of the melt distribution of the liquid inside the reactor. Now, then distribution performance analysis, how you will do based on your that distribution of the liquid. If a variable if you consider that phi, which is a function of x and y, if it is defined as the liquid flux through each tube, and it is designed discrete values, and it is assigned as those discrete values corresponding to the measured liquid mass flow rate for each bottle. Bottle means here where that liquid is collected after distributing, or it is coming out from the reactor at a free identified cross sectional coordinates. Then you can have this equation like this: phi in the x and y direction, it will be a function of mass flow rate liquid, that is liquid mass flow rate, which is coming out from the reactor after distribution. So, by this equation you can actually analyze those performance of the distribution. In this case, A is called that area of each tube or channel in the reactor. So, this equation this concept has given by Behel and Roy in 2007. And according to their observation that and also their that concept that liquid is allowed to be collected over a suitable predetermined period of time, while the gas is allowed to escape through a specially designed disengagement section. After the measurement period, the tray should be withdrawn and the liquid collected in each bottle is weighted using a digital balance. After that, you can analyze those values of time averaged liquid flux that is obtained at pre identified cross sectional coordinates, and then data is to be incorporated over the entire cross section, and a normalized maldistribution factor to be defined such as here it is given here sigma square, that will be equal to 1 by a double integrate of phi minus phi by phi whole square dA, as shown in equation here in the slides, where phi is spatially averaged value of that phi here, which is expressed as like this. So, this phi is equal to 1 by a double integrate of here phi into dA. So, in this case the surface integrals can be evaluated discretely using the available numerical techniques with negligible error, and for a uniform flow the maldistribution factor has a value of 0, and the increasing values indicate a larger deviation from the uniformity. So, you have to remember these things, that when this maldistribution or what should be the maldistribution factor, and if it is coming to 0, then you can get that uniform flow. Next, one of the important that hydrodynamic factor, it is called hold up of the phases. What is that hold up of the phases? Now, if you are considering the two phases like gas and liquid, then what will be the volume of that individual phase that is occupied in that particular channel of that reactor. It is called that hold up of the phases. If you are considering gas liquid hold up in an important gas liquid system, then hold up is an important hydrodynamic parameter for that reactor design, scale up and performance modeling. And in this case, this flow regime that depends on this hold up of that gas liquid system. And in monoliths, the hold up is characterized by the formation of liquid slugs in the channels in a regular fashion, whereas the liquid hold up in the trickle beds and other structured bed reactors arises from rivulets between the particles and the structure. So, this is the difference of that hold up structure or characteristic factors in the monolithic channel and the trickle bed reactor. In the monoliths operating in the Taylor flow, that is called slug flow regime. So, in that case, that liquid hold up you can calculate by this equation, where you can get it from the average liquid slug length and also total lengths of the liquid and gaseous slugs. So, in this case you have to neglect the liquid film that is surrounded to the gas bubbles when the slugs do not coalescence there. So, the ratio between the average velocity of the liquid slugs and the average velocity of the bubbles differs only slightly from 1 there in the slug flow pattern in the monolithic channel. That is why you can directly obtain those liquid hold up from this that slug length and the gaseous slug length. So, average volume fraction of the gas that will equals approximately the ratio of the flow rate of the gas to the total flow rate with a difference of about 15%. So, either you can get it from the slug length of the gas and liquid, or you can get it from the velocities of the that gas and liquid through the channel. Proper measurement of the length of the liquid and gas slugs would give a fairly reliable measurement of the hold up based on this equation. In general, the gas and liquid velocity inside the monolith channel that can be independently varied by changing the gas and liquid flow rates into the system. Therefore, the hold up can be changed either by changing liquid or gas flow rates. Now, as per Zhu et al. Model, they have actually developed one that relationship between that liquid hold up with the operating variables. So, in that case, for the gas liquid system, if gas and liquids are flowing at a certain velocity, you can calculate the liquid hold up from this relationship, that epsilon L will be equal to 1 minus U G S by C 0 into U G S plus U L S plus U D. So, from this relationship you can get directly what should be the liquid hold up. Once you know this gas velocity and liquid velocity, of course, here one of the important factor is called C 0 here. This C 0 is called the distribution coefficient, which actually describe the effect of velocity and concentration profiles within the mixture of the gas liquid, which is flowing through the channel, and also it accounts for the interaction of the velocity and bubble phase hold up distributions. Another factor is called U D. This is called drift velocity of the gas, which actually describes the buoyancy effect, and also it is the effect of the local relative velocity between bubbles and liquid. So, this C 0 and U D that actually depends on the that fluid properties as well as that geometry of the channel. Now, C 0 that is distribution coefficient is actually mainly depends on the ratio of gas and liquid density, and you can calculate from this equation. Whereas, this drift velocity, it is a function of physical properties of the system like density and also that the geometry of the channels, that is hydraulic diameter. So, from this equation you can calculate what should be the UD. So, once you will have this C 0 and UD, you can directly calculate what should be the liquid hold up, and gas hold up simply you can calculate also by this equation here given. So, this is simply that epsilon g is called gas hold up and epsilon L is called liquid hold up. This summation of this liquid hold up and gas hold up should be is equal to 1 for gas liquid system. And another important factor is that pressure drop. Pressure drop is main important factor in that flow resistance to get that different flow regime as well as that mass transfer characteristics there. So, in that case the wall frictional pressure drop, the static head and the acceleration contribution will be there in the total pressure drop. Now, the static head is dominant, which is in direct relation with the liquid hold up in the bed, and neglecting the acceleration contribution and knowing the hold up values, you can calculate the two phase frictional pressure drop with the following equation here given, where FTP is the two phase friction factor and UTP is called the sum of the superficial gas and liquid velocities, where L is called height of the monolith. And according to the Grollman et al. Model given in 1996, they have suggested one correlation based on their experimental data to obtain that total frictional pressure drop based on this equation. So, you can directly obtain that what should be the frictional pressure drop at your particular operating condition once you know that gas and liquid velocity and your physical properties of the system. Similarly, other models also can be used like Mewes et al. Model here, it is given in 1999, that this model actually stated that the total pressure drop will be based on that additional frictional pressure drop of gas phase and the pressure drop that is caused by the liquid vortices in the head of the liquid slugs. Thus, the pressure drop can be estimated from this equation here. And for monolithic loop reactor, you can say that the pressure drop can be predicted using the following formula as given by that Hughes-Wolf et al. So, this also important to calculate that frictional pressure drop here based on this equation. And according to Kritzer et al. 2005, they have also suggested that two phase pressure drop under the Taylor flow condition in a capillary, and in that case the friction factor is a function of liquid slug length, and they suggested a correlation like this here, where psi slug is the dimensionless liquid slug. It is very important to know the and it will be a function of that L slugs and also that slug length and the hydraulic diameter. And a correlation also they have proposed to calculate that this psi slug, that is ratio of that length of the slugs to the hydraulic diameter. And based on this calculation, you can obtain what should be the friction factor for that particular monolithic reactor, where two phase systems are used for that particular chemical engineering process in the slug flow regime. And for the packed bed distributor and square channel of monolith, Zhu et al. Also they have proposed this psi slugs of this ratio of that liquid slugs to the that hydraulic diameter as given in this equation. The nozzle distributor, if it is used, then the friction factor and for the 400 CPSI and for 100 CPSI, they have proposed these correlations to calculate that friction factor. And in this slides, you can have different that pressure drop per unit length as per specific surface area, as per that different surface area, how you can get that pressure drop at a different cell density that you can get from this slides to calculate the pressure drop. And another important factor of this characterizing that monolithic reactor based on that hydrodynamic, it is called that mixing characteristics. In this case, neglecting the proper characterization of the mixing phenomena that can result in considerable error in the reactor performance. And in that case, models such as axial dispersion model, tank incidence model, and attempt to account for the flow deviation from the plug flow characters and to improve reactor performance, you have to analyze that mixing characteristics based on that model. And in modeling monolithic reactor performance, plug flow of the liquid slugs has most often been assumed, and in that case the assumption is made by the fact that in the slug flow the liquid slugs are intensely mixed and there is very little concentration gradient in the either the radial or that axial direction if there is no chemical reaction takes place. Moreover, the thickness of the liquid film around the gas bubbles is very small. So, there is thus no interaction between the two successive liquid slugs in the monolithic reactor, and hence axial dispersion will be minimal. And that can be obtained by the residence time distribution method by tracer techniques, just inserting some tracer and collecting the sample and analyzing that tracer with respect to time, then fitting that concentration versus time data with the that models like this type of models. You have to first draw this that ET, that is concentration versus time data, where you can calculate those that parameter for that mixing characteristics at that axial dispersion coefficient just by fitting this model of this piston dispersion exchange model. And according to this model, you will get that different parameters like that it is defined as per given information in the slides. Some that fraction of the liquid that is dynamic, even some dimensionless parameters here, mass transfer group, and also Peclet number here, dispersion groups here, that is defined in the slides here. So, based on this model, you have to first calculate that what will be the ET, it would be calculated the CT by CT here, it is given here, and then from that model you have to calculate that that by moment method what would be the sigma square, that is called variance of that model, and once you know that variance you can correlate this variance with this Peclet number. That Peclet number will give you that intensity of the mixing, that is 1 by Peclet number, it is called the dispersion number. If you are getting more dispersion number, you may get that more intensity of the mixing inside the reactor, and also degree of mixing. You can say that based on that degree of mixing, you can say what should be the that average residence time of the liquid phase in the reactor, and which actually directly related to the reaction performance and of the chemical engineering process. And also you can say that performance of the reactor based on that mixing characteristics. So, how we can get the intensification of that particular process in the monolithic reactor, you can assess it by this mixing processes. So, you can say that these mixing processes will be actually depending on the several factors like geometry of the reactor, as well as that other operating variables like that physical properties of the system, and also operating variables like flow rate of the phases. Also another important, the distributor type is one of the important factor, because that several distributor will give you that different degree of maldistribution of that liquid inside the reactor, which we may affect that energy distribution in the reactor, how that liquid will be distributed inside the reactor based on that energy dissipation. Now, again that mixing characteristics will affect that mass transfer phenomena, and different mass transfer phenomena like gas liquid solid, and pore distribution here as per slides given, and also different type of mass transfer coefficient based on that gas liquid solid like this. So, here these are the slides that you can go through in more details to get that even for mass transfer coefficient calculation from the correlation, and what are the effects and how that gas solid mass transfer happens, and what are the different regimes of that reaction rates based on that mass transfer coefficient, and also that comparison of that monolithic and packed bed reactors there. So, and also how that energy is being actually distributed, and how to calculate that energy or power input per unit volume of the system to calculate that mixing characteristics and all the, and also the mass transfer characteristics. So, that power can be calculated based on this equation. So, once you know that energy distribution and what will be that efficiency of the reactor, you can calculate. So, I would like to stop here. This module of this that monolithic structure and its use and application, and also different hydrodynamic aspects, and we will start the next lecture onward another module for that process intensification. I would suggest you to go further reading for this monolithic structure and its application, and also different hydrodynamic aspects. These are the some references that will be helpful for you. So, thank you.